It's a nice, very nice setup. So I'll be talking about some recent progress in understanding defects in forestry preambles. First of all, I'd like to apologize to people who have heard another version of this talk as strengths, but I will give a more complete account. I'll give a more complete account of the story here. And of course, because it's a typical seminar, you are welcome to ask questions, interrupt me with questions. So this will be based on 3 recent papers that appeared in the past few months. In particular, the second one with Shota Komatsu, as well as some works in progress. So let me start with some brief observations. The interforestry preamble is perhaps the most well-studied interactive conformal field theory in recent years. This is the case for the following reasons. It shares many features of strongly coupled gauge theories in 4 dimensions. It has a variety of methods which is available to prove its dynamics, such as supersymmetric localization, integrability methods, as well as the conformal bootstrap. It also bears a close connection to quantum gravity on ADS5 times S5, thanks to the ADS-CFT correspondence. And indeed, in recent years, there have been lots of progress in understanding this local correlation functions of local operators in the context of interforestry preambles. And these are the most basic observables in the interforestry preambles as a superconformal field theory. But the interforestry preambles is, of course, much richer than just having local operator correlation functions. They also admit a large family of defects of different codimensions, giving rise to defect observables. These defects are interesting and important observables to be studied. For example, they are sensitive to global structures of the gauge theory, which are otherwise invisible to local correlation functions. They also gave rise to new structure constants for the full operator algebra. And by studying constraint on these new structure constants, say from unitarity and crossing, one can derive some refined consistent conditions on a fully fledged extended CFT. Perhaps the most familiar kind of defect in interforestry preambles are the Wilson loop operators. And these are also known as the order type defects. But more generally, defects in interforestry preambles are of the disorder type. So they're defined by some singularity of the superpreambles fields along some locus in the space-time manifold. This disorder type defects are generally much harder to study beyond perturbation theory, but we'll see how methods introduced in this talk can be used to tackle these more complicated defects. So one can imagine some general program for studying defects in interforestry preambles, and this goes like follows. So first of all, we would like to have some classification of defects, or rather universality classes of defects, the conformal defects in interforestry preambles. So in this aspect, there have been lots of progress made in partial classification of supersymmetric defects in interforestry preambles. The canonical examples are the BPS Wilson to Hooft loops, the Gukov-Witten surface operators, Galto-Witten domain walls. And these defects also have descriptions in type 2B string theory in the large N limit, thanks to work of these authors. And this also gives a potential way to classify at least in the large N limit, defects in the interforestry preambles by studying solutions to type 2B equation motion in the presence of suitable sources. Second, one would like to develop some tools, efficient tools, to extract defect observables. So on one hand, we would like to have some analytic methods that will allow us to solve for the new defect structure constants. Second, we want to combine this with, potentially combine this with the bootstrap philosophy, namely to formulate consistent conditions on these defect observables and explore general constraints from unitarity and crossing. And this bootstrap approach also gives the potential another definition of defects as solutions to some bootstrap consistent conditions. Finally, we would like to explore implications of these defects in interforestry preambles for the structure of the fully extended theory. So in particular, defects of extended defects are typically charged on the higher can be charged under higher form symmetries. And if your theory has a 't Hooft anomaly that involves the higher form symmetry, then such anomaly can manifest itself through volume couplings on the defect. And finally, it will be an interesting question to ask and answer. That is, what is the complete set of data that is needed to fully specify a CFT? In other words, if I hand you a CFT with all the local operator correlation functions and the 't Hooft anomalies, can you say that the extended defects are all completely determined? One way to potentially answer this question is to study the solution to this kind of bootstrap equations. But that will be outside the scope of this talk.
Yifan?
Sorry?
Hi, sorry. Can I ask a slightly general question?
Of course.
Perhaps you will talk about it, but so the question is, what exactly does one mean by defects? Because let's say you focus on some codimension, that's codimension 1, so
yes.
It's some boundary condition. But to that, one can couple some 3D theory with appropriate supersymmetry as well, and thereby giving you an infinite class of boundary conditions by coupling just an arbitrary 3D CFT to it. So presumably, when you define defects, you would like to define it so that you don't allow such an operation. So
right.
what is a rigorous way of saying these words?
Right. So that's a very good question. So there's some proposal in the literature. Well, in some discussions, I'm not sure if it's already in literature, of the notion of a minimal defect. It's precisely the type that that FBJ had in mind, meaning that there's no intrinsic stress tensor on the defect. So that sets it apart from some local 3D conformal field theory on the defect.
But that is one way to say this, that there is no local conform stress tensor. But presumably you can imagine a 3D solutions to the 3D crossing equation with sufficient supersymmetry. You know, yes. Generically it will not have a stress tensor. So in fact, the space of theories with no stress tensor will be quite large. And that's then correct. You can just couple it in some way that you want. And then you could still, you know, this kind of game you could still play with that constraint as well, and presumably allow for even more general things. So I don't know how that addresses this question.
Right. So, but restricting conformal defects would shrink that possibility to a smaller set.
Well, so, conformal defects meaning, I mean, you would couple.
You have to have some conformal coupling, right? You have to have some conformal coupling between the 3D, you know, the 3D operators that you have that satisfy the crossing equations.
I mean, you could flow in the RG flow also. You could flow along the RG flow to give, you know, so that you get some weird thing.
Right. That's right. So I'm talking about your Southern class. You can have multiple flows that flow to the same CFT. Sorry, flow to the same conformal defect.
Maybe one can say that there is no stress tensor, but there is a displacement operator.
Yes, of course.
That's slightly constraining. Okay, fine. Okay, thank you.
Yeah, that's an important question. Yeah, I should say that this bootstrap analysis of this in the presence of defect is still at a rather infant stage for reasons that I'll come to later in this talk. Okay. So let me just say what I will talk about in more detail in this talk. Will be this mostly about the second point, which is to develop some analytic tools to extract defect observables. But I'll also comment down the other points throughout this talk. So let me be more concrete. So let's focus on the defect observables, potentially defect observable in the introversion polynomials with UN or SUN gauge group. So the general observables in the introversion polynomials can be parameterized by this parameter space. So this axis labels the rank of the gauge group. Here, G4 is the gauge coupling, it's usually Yamil's coupling, and I have grouped it with N into the 't Hooft coupling just for convenience. And this axis labels the number of potential supersymmetries that's preserved by the observable of interest. And depending where the observable is on this parameter space, there are different efficient methods that I will present to extract their physics. So for example, if the observable preserves a particular 116 PPS subalgebra of the full PSU 2, 2 the full PSU 2, 2/4 superconformal algebra in for superamines, I will describe some emergent 2D 1D description that allow you to efficiently extract such defect observables. This is this kind of method is efficient on this facet. On the other facet, which leaves a large n, I'll describe some extension of the traditional integrability approach to study defect observables. This kind of approach applies to supersymmetric as well as non-supersymmetric observables, okay, that breaks all the supercharges. And this is the extension of the traditional bootstrap approach in the sense that the traditional integrable spin chain method applies at weak coupling as a weak coupling expansion. But the approach, the integrability approach that I will describe is of the bootstrap type and allow you to extract this kind of observable at finite to Hooft coupling. Okay? And furthermore, there's also the more traditional type 2B string theory approach, which is quite powerful when you are at the large to Hooft coupling, as well in the large n limit. So these darker regions on this facet can be determined this way by some probe-ring analysis in type 2B IDS 5 where the defect is described by this probe-ring. To illustrate these methods, I will apply to the particular case of the defect one-point function. So this is the one-point function of some local operator in the for superamines in the presence of a codimension 1 interface defect that circles the local operator. So I will show that we can determine this kind of observable using all these methods, and the results agree at the common regime of validity. So in the end, we have determined completely this interface defect one-point function on all the dark regions of this parameter space. Of course, one would like to go deeper into the parameter space and completely determine this observable, but that requires some additional method. And that's potentially by this conformal bootstrap method, which I'll comment on later in this talk.
Sorry, Yifan,
Yes.
I guess it will become clear in your talk, but this number of supersymmetry, that is not the number of supersymmetry of the theory, right? The theory that you are working with is n equals 4, but
That's right.
the supersymmetry is preserved by the observable, meaning the operator
right.
with one-point function you want to compute.
That's right. That's right. So
Defect
this
will
is
also be always half BPS?
say it again.
The defect will always be half BPS, or that could also be non-supersymmetric?
The BPS can also be less supersymmetric. That's right. Okay. But the particular application I'll describe to you, the defect will be half BPS, and this defect, this setup will be quarter BPS.
Okay, thank you.
But more generally, this method will allow you to extract the 116 BPS observables, and this method here will allow you to extract totally non-BPS observables.
Okay.
Okay. Thanks for the question. Okay, so let me first get down to the first method that I promised, which is some emergent 2D 1D effective theory, which I'll call defect YAMLs, which is a very efficient tool to extract 116 BPS defect of observables in the inverse YAMLs. So before I talk about the defect YAMLs, I want to review two important previous works that led to the current development. So first is the discovery of a 2D subsector in the 4D inverse YAMLs on flat space or on S4 by a Wang transformation, thanks to the work of these people. So there was discovered that the emergent 2D YAML sector is described as the usual 2D YAML theory, but constrained to the so-called zero instanton sector. This is the 2D instanton sector, not to be confused with the 4D instantons. This is also known as vertices in two-dimensional gauge theory context. The 2D gauge coupling is related to the 4D gauge coupling as follows. You may worry about the minus sign, and that is warranted, and that requires some particular integration contour in this 2D YAML description that's addressed in these papers. The 2D gauge fields in the bosonic YAML theory is emergent from the 4D perspective. I should also emphasize that the 2D YAML lives on the particular S2 of size R inside inverse YAMLs. This R is arbitrary, okay? But R enters into the relation between the the 2D gauge coupling and the 4D gauge coupling. So GMOs, not to avoid confusion, the GMOs here means the 2D gauge coupling. G4 is the 4D gauge coupling. The 2D amuse gauge field is a combination of the 4D gauge fields. This is the 2D gauge field. It's a combination of 4D gauge field restricted to the S2, and also involves a combination of 3 out of the 6 scalars in the interferential amuse theory. And this kind of 4D, 2D correspondence was first conjectured based on the following observation. Namely, people studied observables of 1/8 BPS Wilson loops in the 4D interferential amuse theory, which are Wilson loops of arbitrary contour that lie along arbitrary contours inside the S2 of size R. And they discovered that this similarly complicated observable can be recasted into some form which makes it clear it's just some ordinary Wilson loops in some 2D amuse theory. Okay, so there's some observation that was made in this paper, and later this kind of correspondence was derived by Pastun from localization with respect to a particular supercharged Q that lie inside some SU1/1 subalgebra of the full superconformal algebra. And this supercharged Q has the interesting feature that it squares to a combination of a transverse rotation and perp transverse to this S2 inside R4 or S4 up to a Wall transformation, as well as some R symmetry rotation R5/6. Was there a question? Okay, if not. So this kind of 2D correspondence is very useful and powerful because it reduces a computation of seemingly very complicated interacting observables in the 4D theory to some solvable problem in the 2D gauge theory, which is much simpler thanks to the quasi-topological nature of the 2D amuse theory that you may have heard of.
So, sorry, this Q squared is equal to that. So is that like a Q commutator with an S?
Good question. So here, whenever I write Q, I don't mean it's a Poincare supercharge. So this Q, if you want to represent this Q in terms of the Poincare and superconformal supercharge of the interferential amuse, is a linear combination.
Okay, thank you. So yeah, it would be a linear. There would be a Q and its corresponding S that would have this guy on the right hand side, right? So
well, so if you are very careful, you notice that the dimensions doesn't quite work out. So I have suppressed some power of R here as well. Yes.
Okay.
Yes. Yeah, but you're right. Yes.
Yeah.
That's right. Okay. So let's move on to the next thing that I wanted to review, which was yes.
So if you have a local operator along with the Wilson loop on the left hand side, and that local operator, let's say, happens to lie on the same S2, then can you compute that observable from this?
That's right. So you can have local operators on the Wilson loop. You can have local operators which is on the S2 but away from the Wilson loop. Yeah. Both such observables can be computed from the 2D theory side, and that has been studied prior to the works that I'm going to present here.
I see. Okay.
Yeah. Okay. So let me get to.
Sorry, Yifan, let me understand this S2 better, please.
Yeah.
So is it an S2 with R4?
Say it again.
So I think of R4, and there's is this S2, let's say, a unit S2 in the 1, 2, 3 axis?
Yes. So you just take, say, x4 equals 0, and this S2 is determined by, x1 squared plus x2 squared plus x3 squared equal to r squared.
Okay, and could I also understand the M perpendicular better in this language, please? What is M perpendicular?
So M perpendicular in that flat space language is a combination of K4 and P4. So translation and special conformal transformation in the 4 direction. And if you do the Wall transformation to S4, that becomes one of the killing vectors on S4.
So this combination of K4 and S4 leaves this S2 invariant?
S2, yeah, it leaves the S2 invariant. So the idea is that in P4 and K4, if you remember, K4 has some component that's equal to like 1 minus x squared, right?
Yes.
Yeah, so if you restrict it to the sphere, this component will vanish, and the rest of the component just vanish when you subtract P4 from it, because P4 has like a constant components, just 0, 0, 1.
Okay, thank you.
Yeah, no problem. Okay, so let me now move on to the next previous work that I wanted to review, which is a somewhat parallel story.
Sorry.
Yes.
Just one more question. So this SU1/1, that was the superalgebra preserved by the Wilson group?
So that's a good question. So the most general 1/8 BPS Wilson loop, because it's 1/8 BPS, would actually preserve SU2/1 subalgebra inside PSU to come out 2/4.
Even the wiggly one or the circular one?
So the circular one would preserve a half BPS algebra of PSU to come out 2/4, which is OSP4*/4. But if you have a 1/8 BPS, it doesn't have to be circular. It can take the shape of arbitrary contour on S2. Consequently, the symmetry is smaller, and it turns out to be SU2/1 subalgebra.
I see.
Right, but the fact that you only need a Q that generates SU1/1 means that you can definitely enrich the story here by including other defects, and that's what I will come to. Yes.
Okay, thank you.
Yeah, no problem. Okay, so I was just gonna start to describe this another similar parallel story, but happens in 3D superconformal field theories for supersymmetry. In that case, it was discovered by these authors that there's a 1D topological sector that lives on the grade S1 inside S3. So once again, this is some closed subsector of the 3D theory in the sense that the operator product expansion close among themselves in this 1D sector, and it's conveniently described by some topological quantum mechanics. So to be more explicit, just to give you a flavor of what this topological quantum mechanics looks like. So in the simplest case, this topological quantum mechanics can be described by some free theory with a first order, with the first derivative kinetic terms. And this Q and Q tilde are some scalar fields in this 1D topological quantum mechanics. And they obey some anti-periodic boundary conditions along the circle. Okay. And from the 3D perspective, these scalar fields are twisted combinations of the scalar fields in the free hypermultiplet Q and the lowercase letter Q and Q tilde, and they're twisted such as to leave in certain to preserve some certain supercharge, which I'll come to. And you can make this free 3D 1D correspondence more interesting by coupling the free hypermultiplets to some interacting vector multiplets in the 3D side. And consequently, by a non-trivial RG flow, this coupled system will flow to some 3D for superconformal field theory in IR. And consequently, on the 1D side, you will get some interesting gauged topological quantum mechanics. Okay. And once again, this kind of correspondence which was first analyzed kinematically at the level of superconformal algebra and some protected operator spectrum. It was derived at the level of the path integral by some supersymmetric localization with respect to a supercharged Q 3D, which I'll denote as here. And this Q3D has a very similar structure in that it squares to a combination of a transverse rotation, but now to the S1 inside S3. And some R-symmetry rotation. And this generates a subalgebra SU1/1 inside the 3D superconformal algebra OSP4/4. This localization analysis was analyzed in this paper. And once again, this 3D 1D correspondence is very useful and very beautiful in the sense that gives a way to extract strongly coupled observables in some 3D and 4 theory that may involve, for example, monopoles, the vertex loop operators. And it reduces such a problem to some solvable problem in the 1D operator algebra, which takes form of some mini bootstrap problem along a line. Okay. And what you may have already noticed the similarity in the localization story between the 3D 1D story and the 4D 2D story. And the supercharge used has a very similar structure. So one can naturally ask, can these two pictures be combined into one setup? The answer is yes. Indeed, the OSP 4/4 algebra, which is the superconformal algebra of 3-4 theory, is naturally the superconformal algebra on the half BPS interface in the 4D/4 superMUs. In particular, the subalgebra is embedded as follows, and it's consistent with the identification between the 3D supercharge and the 4D supercharge, which generate isomorphic SU1/1 subalgebras. This very simple kinematic observation actually has interesting consequences in the following sense. So one can study the cohomology, meaning that operators, potentially extended operators in the inverse superMUs, that's preserved by the supercharged Q. And this gives rise to a very rich zoo, which I'll tell you about. And just by general argument, the Q localization, meaning localization of the inverse superMUs path integral with respect to the supercharged Q, in the presence of some defects in the superMUs that preserve the supercharged Q, will give rise to a defect enriched 2D MUs theory. And this effective theory is what I will call the defect MUs theory. Okay, so I will, questions?
Yeah, one question. So I remember vaguely that this 2D Young Mills is somehow invariant under area preserving diffeomorphisms.
That's right.
So that's, where is this coming from? I mean, why is this conformal thing getting the other way around? I mean, this becoming area preserving, invariant under area preserving diffeomorphisms.
Very good question. So let me give you a answer which may not be complete. So I want to emphasize that the area preserving diffeomorphism structure of the superMUs of the 2D MUs is not coming from the superconformal symmetry of the 4D MUs. So it's not some kinematic outcome. Rather, it's coming from the dynamics of superMUs theory.
Oh, I see. But how is it coming? Is that something that can be explained, or it's mystery, or what?
Well, it's a mystery.
I would have thought it's kinematical.
Yeah, it's not kinematic, but yeah, let me, yeah, okay, right. Let's see. Yeah, so one could hope to have such an interpretation potentially from consideration of the entity superspace. So there should be some kind of 3D effective theory that's due to this 2D MUs. But I don't know how to make that precise at the moment.
Okay, thank you.
Yeah, but it's a good question, right? Okay. So I will not tell you the details for this classification of observable in the Q cohomology, but I'll outline the strategy and give you the list. Okay, give you some incomplete list. So we're looking for some we're looking for defects in inverse superMUs that preserve this supercharged Q. So correspondingly, you should preserve this subalgebra SU1/4, and that's generated by Q. In particular, the square of Q, which involves this transfer rotation, as well as some R-symmetry rotation. For simplicity, let's focus on the case where this defect are actually a singlet on the R-symmetry rotation. In that case, the defect, just to preserve Q square, the defect has to lie along some loci in the 4D spacetime manifold, which are fixed by this Killing vector M perp. Okay, so this gives some constraints on what kind of submanifolds of R4 or S4 that this defect query D can wrap. And then the next step is to specify the defects in terms of some potentially singular configuration of the superMUs fields. This happens generally for disordered defects. And you want to tune this singular configurations to preserve supercharged Q. Okay. This kind of analysis has been performed for the half BPS defects. It's harder for this less supersymmetric defects, but they can be done. And if you want to derive this defect YAML description, we also apply the following strategy. First of all, one would like to have some off-shelf formulation as typically what one needs for localization computation. One needs an off-shelf formulation of super YAMLs, but now in the presence of defects. So the off-shelf formulation of super YAMLs in the absence of defects are of course well known, thanks to the work of Pestun, and that's based on previous work from Berkowitz. By introducing some auxiliary fields, by introducing 7 auxiliary fields and modifying the supersymmetry transformations. And that ensures that this action is actually supersymmetric with respect to some Killing spinner epsilon representing the supercharged Q, regardless of using equation motion or not. But the introduction of defects give rise to some complications. And you have to make sure that this variation of this action S under this Killing spinner or this supersymmetry transformation is 0 around this defect insertions. So that puts some constraint on what kind of boundary conditions that you should impose. That's related to the this singular configurations here. Once you ensure this boundary conditions and the possibly boundary terms are such that this variation vanishes, you can run the usual localization procedure. Namely, you need to study the solution to this BPS equations and parameterize the solutions. And by running this whole procedure together, you find that there's some effective 2D YAML theory on the BPS locus, which is described by some 2D YAML theory in the absence of defects. That's the work of Pestun, and here will be decorated by some defects. Okay.
So the first thing you find is that the defect has to be 2-dimensional.
So first thing you find is that effective theory, the BPS locus is effectively 2-dimensional. So it depends on 2 coordinates. So you may be familiar that Pestun had another paper where the introverse super YAML is localized to a 0-dimensional matrix model. That's with respect to a different supercharge. And there you would say the effective BPS locus is just 0-dimensional, just parameterized by some constants. But here you find that the BPS locus is parameterized by a function of 2 variables.
And by defect here, you mean some effective boundary condition for n equals 4 Yang-Mills theory?
That's right. So the boundary condition here, by saying boundary condition, I mean some doesn't have to be codimension 1. So it's some it's a boundary condition for the fields in super YAMLs along the singular locus potentially.
Right. So by your definition of defect, you exclude the kind of thing that Abhijit was worrying about earlier in the talk. Like adding new degrees of freedom to the surface is sort of not considered here.
Yeah, so those can be accounted by boundary terms. So the boundary term can involve some localized degrees of freedom at the defect locus.
So, but if you allow that, you could add an infinite amount of stuff, presumably.
That's right. That's right. So if you add more, so here is not about classification. So here is that if you have a defect, this is the way to derive some effective theory that computes this defect observable. So I would still say that if you have a defect that as arbitrarily described, but coupled to some local degrees of freedom on the defect, that will still be a defect.
So it would be like it would be 2D Yang-Mills theory coupled to some stuff.
That's right. That's right.
Okay. So then it may not be solvable.
In general, it may not be solvable. Yes.
Okay. Right. Yes. Thank you.
So, Yifan, is this what is going on? So in 4 dimensions, you have a 3-dimensional defect, let's say boundary condition. I don't know whether you want to allow for some weird shapes or you want a planar defect, but you have this 3-dimensional thing, and then because the 4-dimensional theory is localizing to 2-dimensional sphere, the boundary condition or the defect is localizing to some 1-dimensional locus in that on that sphere. Presumably, it's the intersection of the sphere with the plane.
Exactly. Yes. And
are you allowing, so because the previous topology, the quasi-topological nature would have allowed you to let the 1-dimensional Wilson line, it was before, to wiggle right on the sphere.
Yes.
So
yes.
would that mean that in 4 dimensions you could consider not just conformal, just this straight planar defects, but even wiggling defects in some way? Or you
So
to be
that's a good question. So that's related to why I said this um, this area preservingness of the 2D MLs is something coming from the dynamics of interverse MLs. So in other words, it depends on crucially the kind of observable you study. So while it's true for the Wilson loops, which is the other type of defects in the 2D MLs, the observable only depend on the area, but it's not going to be true for this this general interface defect.
So everything will be circular.
That's right. Yeah.
I see. Okay, thank
Well,
you.
but there are other. I will not talk about them, but there are also interface defects which preserve this supercharged Q, but take other topology like a torus times S1. But I don't have a complete description of them yet.
I see. And then it will intersect on the S2 on some weird locus. I mean, it would be circular only, right?
I think it will still be circular, but the effective theory will be different. Right?
I see. Okay, thank you.
Yeah. Okay. So you may ask. So what if I run this general procedure? You may ask, like among the most familiar defects that you have learned, say from type B string theory, which correspond to branes in the type 3 string theory, which ones are realized in this 2D, 1D sector that I just described? So let me just give you a list of the somewhat familiar branes in type 3 string theory. So here the D3 correspond to, the D3 on the left correspond to D3 branes that engineer, say, the interverse superamylose from a stack of n D3 branes. And these other branes on the right correspond to the, you can think of as probe branes, which engineer this defect. So if these branes are longitudinal to this D3 branes that give some space filling branes that essentially change the theory. For example, by coupling the theory to some additional flavors and breaking the symmetry, these are the space filling branes. These kind of branes do not fit in the 2D, 1D sector in the sense that they cannot preserve the supercharged Q that I described. But other kind of branes, for example, the D5 brane intersecting D3 brane along 3 directions, gave rise to some interface. So here, by dimension, I mean the dimension that's shared by the stack of D3 branes engineer the interverse superamylose, and the probe brane that engineer the defect. And one can also have surface operators, which comes in 2 flavors in interverse superamylose. One is the most familiar type, that's engineered by D3, another D3 brane intersecting with the D3 branes that's engineered in interverse superamylose. And this corresponds to the usual Glucko-Witten surface operators. And that does live in the 2D, 1D sector of the that I described, okay? That's captured by these 2D amyls. But another type of less familiar surface defects, which is discovered by Harvey and Royston, that come from intersection of D3 and D7 branes. It's a purely chiral surface defect, and that's not captured by this 2D, 1D sector. And moreover, there are line operators which can be engineered by either D1 brane or D5 brane. In both cases, share 1 directions with the D3 branes that engineer the interverse superamylose, and they correspond to respectively Wilson and 't Hooft operators. And they survive in this 2D, 1D sector, meaning that they preserve the supercharged Q. Okay.
So Yifan, can you say a little bit more about the 0-4 defects? How are they described? Do they have some explicit description or what?
Yeah, very, very good question. So as far as I know, there's no explicit zero. I mean, you're looking for some 0,4 description, right? As far as I know, I don't know such a description. So one could hope, as you and I think you had a paper with Sergei Gukov that describes some UV Lagrangian for this Glucko-Witten type surface defect, right? So one could hope such a similar description could arise for the 0,4 case. It will be interesting to work it out. Sorry,
but then right now it's described by boundary conditions explicitly.
Yeah. It's specifically described by the boundary condition. Okay. Yeah, there's only one paper. Yeah, I think there's only one paper on this subject.
When was this old paper or a new one? Roughly.
I would say like 7 years ago.
Something like that.
Yeah, I can send you the reference. Yeah. Okay, so so what does a general 116 bps network looks like in this that preserves the supercharged Q that I described? So here is a picture of S2, which is the S2 where this 2D defect amuse lives. And from the first perspective, I've suppressed two transverse directions. So this 2D 1D sector, which includes this general 116 bps observables, can have say boundary or interface defect operators live at the equator. Okay, it can have surface operators, either transverse or longitudinal to S2. So it can either wrap this S2 or intersect this S2 transversely at two antipodal points. It also includes line operators of arbitrary shape on S2. So these orange lines are line operators. And it can also include 'to Hooft line operators, but on circles that linked with this two-dimensional sphere inside S4. Okay? And moreover, as BG mentioned, there are local operators where you can insert anywhere on this S2. Okay? And there are also local operators which you can insert restricted to the defect role volume. So for all this list, you can have explicit description of these defects such that they preserve this 116 bps subalgebra that I described earlier.
Sorry, Yifan, could you, suppose if you took one example, let's say a D3 with a D5.
Yes.
If the D3 is in the 0, 1, 2, 3, 4, 1, 2, 3 directions.
Yes.
Where would can I take the S2 to be lying in the 1, 2, 3? Is the unit S2 in the 1, 2, 3?
Yes. Yes.
And where is the D5 in these dimensions?
So in that case, the D5 will be in the D5. So okay, let's see. So the D3 is in 0, 1, 2, 3. S2 is at x0 equal to 0, and 1, 2, 3 in that is the S2 in the 1, 2, 3 direction. Okay, and then D5 will be along 0, 1, 2, and the other three direction is 5, 6, 7, say.
Okay, and that's why it would give you a circle of some sort.
Yeah. And it look at x4, x3 equal to 0, so that's a circle.
Right. Okay. Thank you.
Yeah, no problem. Question? Okay. If not, so I was just gonna say that for all this kind of observables, there are explicit description of this kind of defects that shows that they manifestly preserve the supercharged Q off shell that can be used to derive this. And using that description, you can derive the dictionary between such defects and defects in the 2D amuse theory that on this S2. Okay. In particular, as BG and Shiraz both alluded to, the boundary or interface defect in the 4D inverse amuse would map into a boundary or interface defect at the equator on the S2. Okay. And surface operators, depending whether it's if it's transverse to the S2, would correspond to some codimension 2 twist operators in the 2D amuse theory, which impose some holonomy when you go around this insertion. And if a surface operator is longitudinal to the S2, it will Higgs the gauge group in the 2D amuse theory to some Levy subgroup. The type of Levy subgroup is fixed by the type of the Kukul-Witten surface operator. And Wilson loop operators from the 4D super amuse, as I reviewed before, will just map to ordinary Wilson loops in the 2D amuse theory along arbitrary contour S2. The same contour where this 4D super amuse Wilson loop lies along. And more interestingly, the 'to Hooft loops in the 4D super amuse would modify the 2D amuse theory by insertions of unstable 2D instantons in the 2D amuse theory path integral. Okay. So I emphasize again that if you do not have this 'to Hooft loops, the 2D amuse theory, the 2D effective amuse theory that lives on this S2 coming from localization is restricted to the so-called zero instanton sector. And furthermore, local operators will just map to insertion of the field strength in the 2D amuse theory. And there's a similar dictionary for local operators restricted to the defect role volume of the above defects.
So these 2 lines are something that intersect this S2, are they?
It does not intersect. It links.
Not intersect. Link. I mean links. Yeah, I see.
That's right. Yeah.
I see.
The
And even though, sorry, I see, I see.
yeah,
So let's say,
Mhm.
so you
Sorry.
had some, let's say you had a Wilson line and a Tooth line. And
Yes.
Wilson line, you make it live on this S2. And the
Yes.
Tooth line is could either be inside or outside this S2.
It could be either inside or outside S2, but I haven't given the, so in the papers that I published, I didn't give the explicit form of this tooth lines on the S2, but there is such a tooth line as well. Yes.
No, but let's say if you want to model it as an instanton, so the source of that field could either be inside or outside. So that's your linking, right? That's how one is thinking about linking.
Yeah.
Either it
Yes.
could be inside or outside the S2.
Right.
So my question is, the Wilson line and Tooth line by themselves don't link in R4 in 4 dimensions.
That's right. That's
But
right.
somehow when you make this into this BPS framework, the answers differ when they seemingly link or not.
Exactly. Yes.
I see. That's because of the rigidity coming from the BPS conditions.
That's right. That's right. So very similar story comes in the context of 6D theory localizing to some transaminase theory, where M2 branes which do not link but become linked once you go to the 3D transaminase sector. Right.
Thank you.
Yeah. Thanks for the question. Okay. So here, as I promised, I will give you some explicit applications of these technologies developed here. And in that application, I will focus on the interface or boundary type of defects in the presence of possible local operator insertions, as well as some possible local operators insertions on the defect. Okay, so the particular application I'm going to talk about is this DeFi brain type interface, which Shiraz also asked about. So in this setup, so this is I'm labeling the axis slightly different from the way that I described to Shiraz. So here we have a D5 brain that intersect with a stack of D3 brains. They share 3 common directions, which I'll label them by 2, 3, 4. And the transverse direction along the D3 brains, which is transferred to D5, is x1. So the D5 is located at x1 equals 0. And because D3 brains can end on D5 brains, so we can have a different number of D3 brains on two sides of the D5 brain. So they differ by k number of D3 brains. There's also a dual picture of this brain setup, and that's coming from replacing the D5 brain by the NS5 brain. And the NS5 brain would have to extend in 3 other transverse directions as opposed to the 8, 9, 10 directions extended by this D5 brain to preserve the same supercomplement algebra. Okay, so this is the brain picture, and there's also a field theory description, explicit field theory description of this kind of interface in terms of the super-Yamils fields. Because there's a different number of D3 brains, naturally the interface, D3 brains on both sides of the D5 brain, naturally the interface interpolates between super-Yamils theory, say UN versus UN plus K of different ranks, but the same coupling. And the explicit description of the interface can be described as some singular non-pole configuration of the super-Yamils gauge field, the super-Yamils fields. So let me split the 6 scalars in the super-Yamils theory into 2 triplets, X and Y. This interface imposes some continuity conditions on most of the super-Yamils fields, such as the gauge fields and the Y scalar fields, but allow some simple pole for the X fields as we approach the D5 interface from the right. So this blows up in that limit. The dotted entries are unconstrained, but satisfy some regularity condition. So this polar matrix T is not arbitrary. It's constrained so as to preserve the half BPS supersymmetry. And the constraint is very simple. It just takes the form of some SU2 commutation relation, which demands this T, which is a K by K block, to furnish a K-dimensional representation of SU2. And as you know very well, up to a UK gauge transformation, you can, for example, put the third component of this triplet of matrices into this diagonal form. And this is what is typically referred to as the non-pole boundary condition or non-pole configuration in the introverted preambles. Okay. So this non-pole description is very explicit. It's a very explicit description of the interface defect, but because it is actually pretty hard to use to do any extra computation and finite coupling. It's because it's of this other type. But luckily, there's a useful Lagrangian description, thanks to the work of Gaut-Witten, where it was described that there's actually a 3D UV Lagrangian theory, which I'll call interface theory, which takes the following quiver shape. This Lagrangian theory, as they explain in this paper, this Lagrangian theory will flow in the IR to some superconformal, to the superconformal non-pole configuration. Okay. You can interpret this Lagrangian, you can interpret the Lagrangian from this quiver as follows. Each of these circled nodes denotes a unitary gauge group whose rank is given by the number in the circle. And each edge connecting a pair of nodes denotes a bifundamental hypermultiplet. There's a very similar story in the context of surface operator that BG and Sergei Glukov worked on. Importantly, this quiver gauge theory has a symmetry enhancement under RG flow. So there's a manifest family of U1 symmetries that's coming from the topological U1 symmetry associated with each of these nodes. But thanks to monopole operators under RG flow, the global symmetry of this quiver gauge theory is enhanced to this non-abelian group UN plus K times UN. This enhancement is crucial to be coupled consistently to the 4D superamorphous gauge fields in the bulk. In particular, the coupling is very simple, just by gauging the boundary modes of the UN plus K superamorphous with this UN plus K symmetry. So essentially, you are gauging this 3D global symmetry by some 4D gauge fields, and similarly for this UN factor. And by this gluing construction, one has a UV Lagrangian for the superamorphous on S4 that's coupled to a d-phi brane interface located at the equator. And this UV description manifestly preserves the supercharged Q, which we need to run this localization procedure to give the 2D amorphous description, potentially with defect decorations. Okay. So just to be a little more explicit about this interface theory, you can derive through some gluing construction a matrix model for this interface theory. So this should be thought of as the 3D into 4 theory, say S3, where the interface theory lives. This S3 is the equator of the S4. And by carrying out the matrix model integrations, you can derive this following expression. What's important are this. What's important is that it's this dependence here, which essentially parameterize the UN Coulomb branch VEVs and the UN plus K Coulomb branch VEVs. And these VEVs are the things that you need to glue with the Panin function of the superamorphous on the two hemispheres with dirichlet boundary conditions. Okay. So with this general framework in the presence of d-phi interface and that preserved the supercharged Q.
This theory in your last transparency that was in three dimensions.
Yeah. So this is the matrix model coming from this interface theory, which lives on this equator. So it's you can interpret it as the S3 Panin function of this interface theory, this expression.
Okay. Thank you. Yes.
Yeah. Okay. And with this construction, you can run this with the setup that manifestly preserves supercharged Q. You can just run the localization procedure. And what one discovered is an effective 2D 1D path integral that captured this sector. The 2D 1D path integral involves some 2D degrees of freedom, which are this A and curly A and curly A prime, which are the 2D gauge fields that lives on the two hemispheres. And as you would expect, there's some degrees freedom that's coming from this defect insertion that lives on the equator of the S2. Okay, they are parameterized by Q and Q tilde schematically here. And this 1D and 2D degrees freedom are coupled together by this action of this topological quantum mechanics, which follow from this quiver, but it's rather complicated, so I'll not give the explicit form here. And the super Yamils, the 2D actions are very simple, just the usual 2D Yamils action on the two hemispheres. And with this 2D path integral, 2D 1D path integral in hand, we're ready to use it to compute any general 116 pps of observable in the super Yamils theory in the presence of D-fiber interface, which is taken into account by this this coupling and this degrees freedom in the defect Yamils theory.
Why do you have two 2D angles? What's this explain?
Yeah, so I'm splitting the degrees freedom on the two hemispheres. So you can instead of writing this way, you can group them together. So so here this part describes the action of the 2D Yamils gauge fields on one hemisphere, and this is describes the dynamics of the 2D Yamils gauge fields on the other hemisphere.
I see. And then these two hemispheres are cut by the.
That's right. They're coupled together. That's right. Good. Yeah, no problem. Okay, so let's now apply this this machinery to the particular example that I mentioned, which is the rather basic observable in the presence of interface defect.
Is this Q matter charged under this 2D angles is UN 2D angles?
Yeah, so the very good question. So here I was not writing down all the expressions. So this gauge fields are UN. This gauge fields are UN plus K. This Q and Q tildes are bifundamentals under UN times UN plus K, essentially.
Okay.
Yeah.
Yes, thank you.
Yeah, no problem. So the most kind of basic observable in the presence of interface defect. Yes.
Could you say some words about this topological quantum mechanics? Are they closer more to the quiver description or the zero-dimensional matrix model description?
Say it again.
This one topological quantum mechanics, how does it look like roughly? Is it how like how is it described? Is it like a quiver description? Does it follow from the quiver description?
Yeah, it follows from the quiver description.
No, I mean, sorry. I mean, does it have a quiver description of its own, or it's a simpler description?
It has a quiver description on its own.
I see.
Yeah. Okay, so essentially, for each bifundamental hypermultiplet, so I'm being quite schematic here. So for each bifundamental hypermultiplet, you have a Q and Q tilde.
Mm.
Right.
Mm. Okay.
Yeah. Okay. Right. So let's now apply this machinery to the case of the simple observable, which is the defect one-point function, namely one-point function of some local operator in the presence of interface or boundary defect. These are rather basic structural constants because higher point correlation functions of local operators in the presence of interface or boundary defect can be just determined from these basic structural constants by first taking OPE in the bulk and then expand into this basic blocks. The one-point functions of local operators themselves in the presence of a defect is also highly constrained by conformal word identity. For example, if your operator carry any spin, this one-point function, if you have a primary operator that carry any spin, this one-point function will necessarily vanish thanks to the conformal symmetry, residual conformal symmetry. And furthermore, if you restrict your operator to be a scalar, the dependence on the insertion, the position of insertion X would also be fixed. So through this factor S perp, which is essentially the distance between this operator O and the interface that surrounds it, the interface defect that surrounds it. So all the physics is just contained in this coefficient, which I've circled here. So to be more concrete, let's focus on the case where this operator O is given by some half BPS operator of dimension J and carries some R charge J. So this operator can be represented in the Lagrangian language by some single trace operator, let me just focus on a single trace example here. By a single trace operator, which is built out of 2 of the 6 scalars in the superambiguous theory. And from the general dictionary that I presented before, the one-point function of this operator in the presence of this interface defect, say of the D5 brane type, is simply computed by this 2D 1D path integral, but now with the insertion of the field strength to the power j. Okay. This is from the general dictionary, where local operator insertions in the superambiguous theory gets replaced by field strength insertion in the 2D ambiguous theory. And the strategy to compute this observable from the 2D 1D perspective is just to first integrate out Q and Q tilde. And this gave rise to some gluing condition. It essentially modifies the measure for this 2D path integral. And by some standard 2D gauge theory techniques, because this 2D ambiguous theory is quasi-topological, thanks to that simplicity, you can reduce this right-hand side to some matrix model expression. So let me just present to you the results. So the one-point function of a half BPS operator in the presence of an interface D that interpolates between UN and UN plus K superambiguous theory. The K parameterizes this difference between the ranks. Has this simple matrix model expression, which is a matrix integral over n by n Hermitian matrices. This AI or AJ are the eigenvalues of this Hermitian matrix. This delta A is the familiar Vandermonde determinant. And this insertion in the square bracket is basically coming from this, this insertion that we started with. Okay, it's a degree J polynomial in its eigenvalues, AJ. And it's related to the usual Chebyshev polynomial by the Graham-Schmidt procedure. There's also this one-point function of the interface itself in the absence of any defect operator, in the absence of any bulk operator insertion, which takes a similar form. And this is also related to the so-called entanglement entropy in the presence of an interface. Sorry, it is related to the so-called interface entanglement entropy. So it computes the entanglement entropy in the presence of interface in the superambiguous theory. Okay, and if you want to get to the normalized one-point function of the bulk BPS operator in the presence of this half BPS interface defect, you just simply take the ratio. So we can be more explicit in the larger limit thanks to the saddle point approximation. And indeed, the answer looks very simple and by solving them, because we can solve the matrix model quite explicitly. The one-point function, the same one, so this one-point, okay. So I have here, I'm sorry, I've dropped this defect here, but it's the same observable that on the last slide. It had received contribution from an integral and the sum. The integral takes this following forms, depending whether k is even or odd. K is even or odd. The g here that appears is related to the square root of the 't-Hooft coupling. And the sum has an interesting structure. It's a sum over k terms. And the physical interpretation of this sum structure will come to later in the integrability part of this talk. But I also want to point out that this variable xs is the so-called Joukowsky coordinates, Joukowsky variables, which is related to the subscript in this following way that depend on the 't-Hooft coupling. And this kind of coordinates shows up quite often in integrability literature. And this is already a hint for this D5 brane being some integrable boundary state in type 3 string theory, which we'll discuss later. And with this rather explicit results in the larger limit at arbitrary 't-Hooft coupling, there are simple checks one can do. First, one can expand in a small lambda limit and check with perturbation theory and disagree with previous results, which were computed by hand up to one loop. Quite heroic computation. But more interesting are checks with type 3 string theory in the strong coupling limit. So in that case, we look at the large lambda limit, and the theory is due to classical type B string theory on ADS 5 times 5, where the metric can be written as follows. These x are just identified with a space-time, with the boundary space-time coordinates, and these y's, there are 6 of them, and these are essentially identified with the scalars phi I, the 6 scalars in the superambiguous theory. The interface defect that I described, parameterized by that's given by d5 brane interpolates between un and un plus k super MOS theory would correspond to a probe d5 brane in this geometry, wrapping a submanifold ADS4 times S2 with k units of world volume flux threading this S2. Okay, so this is coming from the fact that k d3 branes dissolve into the d5 brane, into these fluxes. Okay. And then to compute the one-point function of half BPS local operator in the presence of this interface defect, just correspond to, in the type 3 string theory, to extract some world volume couplings on the d5 brane to closed string KK modes. So this amounts to studying the dBA action of the d5 brane, which takes the following form, including Y-null coupling, and the tension goes like follows on this geometry. Okay. So more explicitly, the one-point function will take the following form. So it will involve this world volume couplings, which can be extracted here by expanding this all these terms to the first order in the fluctuation of this closed string KK modes. Okay, so you expand all the fields here around this background with to first order in the fluctuation. This is that, and then it also involves this bulk boundary propagator because we're talking about a vertex, a bulk vertex that's supported on the brane world volume where right. Okay, this is the bulk boundary propagator that's propagating from the brane world volume to the boundary insertion of the source. And then there's the actual factor that take into account the internal wave function. Okay, so if we have if this OJ operator is represented as follows in the Lagrangian language, in the super MOS Lagrangian language, the corresponding wave function on S5 takes the following form. Okay? And this is the very simple integral you can do, and the answer looks like follows. Here, this CJK is essentially the structure constant that coming from this one-point function. Let me emphasize again, the position dependence of this one-point function is completely fixed. What's important are the coefficient, and this is the expression for the coefficient, where kappa is related to the k that parameterizes the defect and the 't-Hooft coupling as follows. And if you want, you can expand this out in the 1/λ expansion, and it takes the following form. And the coefficients are very explicit, but I will not write it here. And indeed, this expression matches with the matrix model results from localization in a large lambda limit. Okay, there's something else that I can tell you, which is some other kind of observable that's captured by this defect MOS theory, namely the defect bulk two-point functions. So as I emphasized, this Q cohomology in the super MOS theory is rather rich. It contains not only operators, the defect operators, as well as local operators on the S2, but it also contains operators that are restricted to the defect world volume. Okay. For example, if you have a half BPS interface in the super MOS theory that lie along this equator S3, then the Q cohomology includes half BPS operators that are intrinsic to the defect, okay, that lie along a line on the interface defect. This is essentially where this is essentially the 1D topological quantum mechanics sector of the interface theory on this half BPS interface.
So, Yifan, do they need to be local operators on the 3D in the 3D theory, or could there be defects in the 3D theory as well?
That's right. So in general, it could also be defects in the 3D theory, such as Wilson loops and so on. Yes. But here, for simplicity, I'm focusing on the local operators, right? Okay, so the most kind of fundamental observable you can build out of local operators in the bulk and the local operators restricted to the defect are the so-called bulk defect two-point functions. So the two-point function O and S. Okay, so 0 here means that it's restricted to defect. X1 equal to 0. Once again, this two-point function is highly constrained just by the residual conformal symmetry. The position dependence is completely fixed, just like in the case of one-point function. And the dynamics is just containing its coefficient C. Okay. And there's a similar version if you do a wire transformation for the two-point function on the hemisphere. this kind of structure constant COS will be important to study the bootstrap problem for two-point function of bulk operators, which I'll explain now. So so there are various kinds of bootstrap problems that one can formulate in the presence of a codimension one in the presence of a defect conformal defect in the conformal field theory. A particular useful one, meaning that has strong constraints, is coming from the so-called bootstrap of the two-point functions. Say two-point functions of two-point function of the same scalar operator in the presence of a codimension one interface. The structure of these two-point functions is almost fixed just by the residual conformal symmetry up to this function g of C. C is the cross ratio which is present thanks to the kinematics, similar to the cross ratio that you have in four-point functions of local operators in the absence of any defects. And it's some combination of the positions of this local operator insertions that is invariant under the residual conformal symmetry. And the bootstrap equation takes the following form. So if you look at this two-point function, you can either take a bulk OP, so-called bulk OP limit, meaning that you fuse these two operators, you expand into other local operators in the bulk O prime, and you sum over all kinds of you sum over all these one-point functions of O prime in the presence of this interface defect. And such things will be determined by HO prime times some conformal block, one-point conformal block associated with this defect. But you can also do it differently. You can take the so-called bulk to boundary OP limit first, meaning that you expand a given bulk operator in terms of local operators Curtius on the defect, and then you fuse this defect operators together. Okay. And here, this other structure constant C enters. And consistency of the conformal field theory requires the left-hand side and the right-hand side to be equal. And the reason I'm saying that this equation is give you stronger constraint than others is because generally, because of the lack of symmetry, there's no convenient positivity for this kind of bootstrap equations in defect bootstrap, except for this case where you have the same operators. Because here there's a positivity here coming from essentially this coefficient will appear squared. I should have squared it, but I guess you see what I mean. Okay, so potentially with this defect structure constants, which I've shown to you, that can be extracted from localization and later from integrability approach, similar for this coefficient, one can feed this data into the bootstrap problem to get bounds on other other OP that enter into the bootstrap equations, like anomalous dimensions, for example. Okay. So just to be a little more explicit about this kind of how to extract this kind of structure constants, and this is largely some work in progress. Some preliminary results was presented in this earlier paper, but largely work in progress. In the case of K equals 0, where the interface theory is particularly simple, it's just described by some free hypermultiplet that glues this, just by some free hypermultiplet that lives on the equator of the UN super-Amuse theory. In that case, the hypermultiplet gave rise to this additional hypermultiplet gave rise to defect operators on this interface, which is some bilinear gauge invariant. Which is some gauge invariant bilinear input of the hypermultiplet scalars. And from this general dictionary I described before, this defect bulk one-point function again gave rise to has some matrix model expression, where this bulk operator insertion again corresponds to this polynomial insertion in A of the Chebyshev is related to the Chebyshev polynomial. But more interestingly, this defect operator will correspond to some will give rise to some hypergeometry. Give rise to some hyperbolic function insertions of the eigenvalue. Okay, and one can solve this matrix model again explicitly in the larger limit, and this matches with the expectation from type B string theory in the strong 12th coupling limit. And there's a straightforward generalization to more general interface defects and more general operators S, and this is part of the work in progress with Shota. Okay, so that's all I'm gonna say about this localization approach. Okay, how good, how much time do I have?
Well, how much do you need?
I think I'm taking too much liberty on time.
It's 1 hour 13 minutes, 1 hour 20 minutes or so now.
Okay.
How about 10 more minutes?
Yeah, so let me just say briefly the ideas without going into the technical details. So there's a complementary approach to analyzing these defect observables. Okay, this is the bootstrap approach which I'll talk about for interface defecting for superamials. So the idea is that these defects in the larger limit, because the superamials is due to type 2B string theory. Okay. Yeah, because the defect is due to type 2B string theory, this boundary and the interface defect on the boundary will correspond to some boundary states for the world sheet string. Okay? Traditionally, this kind of boundary states is described by this spin chain approach, which really boils down to some analyzing dilatation operators in the gauge theory. So in that case, the single trace operator can be represented as a spin chain. So here I'm focusing on the single trace operator built out of two complex scalars in the superamials, Z and Y. The case when the spin chain only consists of the Z letters correspond to the ground state of the spin chain. And the case where you insert additional Y letters, which correspond to so-called magnons, will give rise to excitation of the spin chain. And there's a prescription that tells you how to represent boundary states or interface defect in terms of the matrix product state on the spin chain. And then this local single trace operator will correspond to some beta eigenstates of the spin chain. And then one point function is computed by the overlap, but this method is limited to weak coupling because in the spin chain description, the spin chain Hamiltonian is restricted to nearest neighbor or next to nearest neighbor interactions. But this is some notion that that doesn't make sense at a finite coupling because all sides will be eventually connected once you turn on.
Yifan, I don't quite understand how is it that the defect is given by a state in this. I thought this is some long operator, right? Local operator. And now what does it mean that D is represented by a matrix product state on this in this spin chain or some other?
Yeah, so this defect is represented by a matrix product state on the spin chain. But it doesn't, I mean, it doesn't look, it's a very different state than the kind of states that correspond to this single trace operators.
I mean, does this mean formally in the sense that if you compute overlap of D with O, you get one point function of O in that way, in that sense, it's represented by a matrix product state by some state or
well, I mean, well, so doing perturbation theory, you observe explicitly that this defect is represented by a matrix product state. Okay.
Don't quit.
So how would you do? How would you compute the one-point function of local operators? So as I described to you, this defect is represented by some singularity for the gauge fields, right? Sorry, singularity for the superamorphous fields. So the way you compute the one-point function to the tree level is just to evaluate your operators on this configuration. Okay. And then it was observed that there has a structure of a matrix product state in the spin chain language. And then people have worked to higher loop order and see that this matrix product state structure actually persists.
Okay, thank you.
Yeah. I should say that most of the things in the integrability literature assumes integrability holds to all orders. It's not something that we can prove. But with that assumption, there have been a lot of physical data of superamials that have been produced and matches with various other checks. So it's a strong indication that integrability does hold quantum mechanically to all orders, but to all orders in the 12th coupling, but strictly in the larger limit. Whether integrability holds in some form beyond planar limit is still open question. Okay, so perhaps a more physical picture Well, so as I said, there's some limitation of this traditional spring chain method because of the weak coupling assumption of weak coupling. But there's a physical setup that naturally allow us to graduate from this spring chain description. That is the integrable field theory. Okay, that take into account indefinite number of these magna insertions, for example, and finite coupling effects. Okay, and this integrable field theory actually has a very nice origin. It actually arises from the type 2B string theory on ADS5 PES5. So as I said, the DeFi brain interface defect will correspond to a boundary state of worldsheet string theory just by, this is by definition of a D-brain essentially. But what's nice about this type 2 string theory on ADS5 times S5 is that there's a convenient description in the Green-Schwarz formalism. And if you take the light cone gauge, thanks to the self-dual 5-form flux, what you get is a massive integrable field theory, but it's non-relativistic. Okay. And this picture, all the things that people like about integral spring chain has a close cousin in the integral field theory description on the worldsheet. For example, the magnons, which just correspond to massive particles on the string worldsheet. Okay, again, the Green-Schwarz light cone gauge. The rapidities, which keep track of the Y insertions in the spring chain language, correspond to physical momentum of this massive particles. And R charge will correspond to the effective length of the string, on the, basically the length of the closed string, as seen by a massive particle. And one-point function in the super MOs in the presence of this interface are simply computed by some overlap between closed string state, psi, that represents single trace operators, and this defect boundary state. Okay. So now there's a question or some conjecture one can make, which will be very helpful, which is that is this boundary state integrable? So we have some integral field theory. We can describe this one-point function as some overlap between states in the integral field theory, essentially some cylinder diagram. If this boundary state actually preserves integrability, then we can use the integral structure of the integral field theory to bootstrap this kind of observable. Okay? So there are some, because I don't have much time, I just say that there are some evidence for this integrability of this boundary states coming from weak coupling results from the spring chain. Okay? And from now on, we'll assume that this boundary state is indeed integrable and carry out the bootstrap procedure. So the bootstrap philosophy goes like follows. So first of all, integrability implies that this overlap or this one-point function between the closed string state and the boundary state would factorize into two particle overlaps. So overlap between the boundary states and two massive particles that are going in and out. A U bar means flipping the momentum. And then one want to explore, because these are the basic building blocks for this overlaps, one would explore symmetry constraint on this overlap coming from the symmetry of the setup, the defect one-point function. The symmetry that's relevant here is this SU2/1 squared subalgebra of the more familiar SU2/2 squared subalgebra that's familiar in the integrability literature. And this is the algebra that's preserved by two-point functions, two-point function of BPS operators. This is the algebra that's preserved by one-point function in the presence of an interface defect. And then we want to, on top of the symmetry constraint on these two particle form factors, we want to impose additional consistency conditions. This is coming from the integral field theory. First of all, there's this boundary Yang-Baxter equation, which tells you that whenever two particles are crossed, you have to pay a price by S matrix. Each black dot denotes a block 2 to 2 S matrix. And there's also the boundary unitarity constraint, which says that, the easiest way to understand is to rotate a picture by 90 degrees. And here, this particle propagating in the intermediate channel are summed over. So this just correspond to insertion of resolution of identity here, okay? And there's also the Watson equation, which says that whenever two particles cross, you have to pay a price by S matrix, okay? I emphasize that these are axioms of the integral field theory, and they will get modified if you consider non-integral scattering processes. And you can solve these constraints. You can solve these constraints, and by that you solve the bootstrap problem. And you can determine this one-point function of some general non-BPS operator, which looks like it follows. Once again, the position dependence is completely fixed, and the physics is just contained in the structure constants. I feel again that these are non-BPS operators. And this structure constant takes a rather simple form in the so-called large J limit. So let me emphasize again that the J corresponds to effective length of the string. And in the large J limit, there's a so-called wrapping correction that coming from virtual particles going around the string, whose contribution goes like e to the minus J times mass. Those contributions will be suppressed in the large J limit. Okay. So if you focus on a large limit, you get this very simple expressions. The details is not too important. I just want to emphasize that these expressions are exact in 't-Hooft coupling. Okay, they're non-perturbative as opposed to the as opposed to the answers from the usual spin chain method. Second, the structure constant takes the form of the sum structure. It's a sum over k states. This k states actually form SU2 multiplet of size k. The SU2 is the SU2 R symmetry that I mentioned before, which is a part of the supersymmetry that's preserved, part of a superconformal symmetry that's preserved by the high-PPS interface. And from the integrability approach, this k multiplet of boundary states can also be seen as boundary states, bound states between bulk massive particles and a particular boundary state. Okay. In other words, if you look at the two particle overlap with a particular boundary state, there are poles in the rapidity variable. And if you zoom on the pole, you get a new boundary states. And we showed that such procedure closed after you go k steps, and that k minus 1 steps, and that gave rise to this k multiplet structure of this boundary states. Okay.
So this means that the Levy subgroup classification is coming out. Is that so?
Right. Yes. So if you consider more general D-fiber interface, you have multiple. Yes, and that's associated with the Levy subgroup. Yes. So here, the
bootstrap procedure is giving you precisely the defects that we had before. It's reconfirming right. that is the only stuff that is integrable.
That's right. Precisely. Yes. That's right. Okay. And there are simple checks you can do with this expression in hand. So for example, you can check with supersymmetric case. In that case, so let me emphasize again, also this coefficient is the Joukowsky coordinates, which already appeared in the localization formula. And you set m equal to 0, and many of this factor just collapse, and you just recover the localization results, the sum part, which is dominating this large J limit. And one can also check with the spin chain prediction, the spin chain results in the weak coupling expansion, and this everything perfectly matches. And there are some recent checks in this paper. And to go beyond this large J limit, so emphasize again, these expressions are large J limit. They include all the 1/J corrections, okay, but does not include the non-perturbative corrections in J. Those non-perturbative effects will coming from this virtual particles, massive particles going around the circle. They're so-called wrapping corrections. Those corrections can be taken into account by a careful TBA analysis combined with analytic continuation. Okay, so let me just summarize. So here I present to you a toolkit for studying defects in inverse PMUs. So one of the tools I presented is some localization procedure that allow you to study general 116 BPS observables in inverse PMUs, arbitrary coupling, but otherwise preserve a particular 116 BPS algebra, and such observables are determined by a simple 2D defect YAML's description. And on the another complementary approach that I've introduced is this bootstrap approach to integrable boundary states that correspond to the defects in the gauge theory. And this approach allows you to compute non-BPS observables in the presence of an integrable boundary state that correspond to the defects in a larger limit, but for arbitrary gauge coupling, 't-Hooft coupling lambda. Okay. And I've also illustrated this method in the context of simple observables in the defect setup, such as interface defect 1-point functions and some results about the bulk defect 2-point function. So since I'm running out of time, so here I just flashed the last slide for some, there are a lot more future applications. So I'll just flash the last slide, and maybe we can, yeah. So I'll stop here and invite questions.
Okay, let's first thank Yifan for a very nice, wonderfully clear talk. Questions?
Oh, it's gone now. Ah, now it's gone. Now it's gone.
Any questions? Okay, maybe I can ask one question.
Yes.
So here we have presented a computation of 1-point functions. I mean, you know, the defect bulk 2-point functions, as well as in particular 1-point functions, let's say, of the bulk operators in the presence of defect.
Yes.
So how about computing 2-point, you know, two defect correlation function?
Yeah. So here, so this is not something that's that's included in the present paper, but it's some work in progress. For example, the 2-point function in the presence of a surface defect, the link to its line defects.
No, I mean more general. I mean just simply two interface defects, which would be two circles on the sphere. And if you compute that, then the results about the 1-point function would be obtained in one shot, right? You compute that and decompose in terms of conformal blocks and read off these things. So how difficult would it be to compute, let's say, two circles corresponding to the codimension 1 defects?
Yeah, so that's a very good question. So I have to say that from my previous analysis, I didn't find a setup that allow you to have two defects on two different circles where preserving the same supercharge.
I see.
So that have to be worked out.
But what is weird is that, you know, you are obtaining pretty much the data necessary to compute this observable, right? You are able to obtain all 3-point functions. So you might as well glue them and compute this 2-point function of defects, but not the observable itself. This seems a bit funny to me. So
yeah,
I
but
think that this should be doable somehow, but because the same information is coming out.
But you see, I didn't obtain all the this 1-point function, right? So I obtained for the BPS operator, the arbitrary n, arbitrary lambda,
Right.
and for larger n, I have the single trace operators 1-point functions, not the multiple ones. So it's corners of almost all the results. And by studying the bootstrap setup that you pointed out, we can potentially determine the other missing 1-point functions.
Right.
So
okay. Thank you. Good. So yeah, now I can see that this will not be possible.
Yeah. Right. So that's another way to see it. Yeah, I agree.
Thanks. More questions?
Do these defect observables differentiate, you know, global structures of the gauge group?
Yeah, very good question. So that's related to the first point, which I didn't have to talk about. So in the absence of, okay, so this is not just the defect. So okay, so there are two things I can say. So first of all, if you consider this setup, so surface defects linked with line defects, this will be sensible to the global structure of the super Yamil's theory, the structure of the gauge group and the corresponding one-form symmetries, because the surface defect, some kind of surface defect are actually the one-form symmetry generators, the topological type Gukov within surface operators. But there's another comment I can make is that if you consider the setup on, say, space-time manifold with non-trivial topology like RP4, even in the absence of any defects, the Patin function will depend on the global structure of the gauge group. This appeared in the more recent paper that I wrote. So if you remember the classic Gaussian matrix model that arises from Enclosure PMOs on S4, the answer just looks like it's just the integral of the integral. It's just a Hermitian matrix model for UN matrices. And there's nowhere to be seen the global structure of the gauge group, right? Only depend on the algebra. But this is not the case anymore if you are on RP4.
So can you use the expectation values of these defect operators as a check of S duality of n equals 4 Yang-Mills theory?
Yeah. So okay, very good. So this is related to this comment I was going to make here. So indeed, so the defects what's more non-trivial for these defects than local operators that they transform quite non-trivially under S duality. So the case of Wilson loop versus Hopf loops was studied by many people, but for this general like interface defect, that's less known, but it can be studied. Yes.
And there you would get, for instance, that SUN would map to SUN mod ZN and so on.
Right.
You'd be able to
That's right.
Right.
Yeah.
Along with the transformations of the defect itself.
That's right.
Itself. Yes.
That's right.
There are papers by Gayoto and Witten on this duality of the boundary condition.
That's right. But they're not super careful with the global structures.
I see.
Yeah.
Okay.
Yeah, there's something that I find it kind of exciting is this potential classification of integral boundary states in type 2B string theory. So we always say type 2B string theory on ADS5 times 5 is hard because there's no convenient conformal field theory description on the worksheet, right? There's some super cool proposal, but it's not very useful. So this makes it very difficult compared to the flash-based case. But there's actually one plus that we get from putting type 2B string theory on ADS5 times 5, which is what I emphasize, that there's a massive integrable field theory description on the worksheet in the light gauge of the Green-Schwarz string. So
description is something that the integrable, in the context of just not defect states, but just single particle, and bunch of particle states has been looked at from the integrability community, right?
Yes. But it has, more generally, you can study the kind of brains in the integrable theory, just like
in the massive theory, right?
Just like you do for brains, by solving Carty condition in the worksheet CFD, you can do the same thing for integral brains in the integral field theory, and this would be a much easier way to solve problem like d-incident contributions in type 2B. I mean, as she and Ashok has talked about, I mean, computing d-incident contribution is such a nightmare already in sequence string.
So I don't understand how is it that you're getting information about instantons?
So the d-incident will correspond to a particular boundary state for the integral field theory. Okay.
I see.
Okay.
Oh,
and
you just mean I see.
And one can hope to bootstrap this form factor associated with the instant boundary state. First thing to bootstrap probably the one particle form factor. And once you have this form factor, you can integrate this form factor over the moduli space of the instanton, and that will give rise to contribution to various observables like 4-point functions and so on.
So to your when you did your bootstrap program, what inputs went into that program?
What inputs?
You have to tell it about. Sorry.
Say it again.
When you did your bootstrap program, what inputs went into it? How does it know that you are looking at interface defects and not some other brains?
Right. So that's coming from the symmetry. This is symmetry. So the instanton, for example, would preserve a different symmetry.
I see. Okay. So you would want to preserve some other symmetry and then run this machinery again to see what comes out.
That's right.
Could I ask what's probably a very vague question, but let me ask it anyway. You did localization from the boundary, and you got these results. Is there any chance one could try to do some sort of bulk localization?
Very good. Yes. It's something I have dreamed about, but unfortunately, I don't have any concrete proposal at the moment. Yes, but yes, but you see, something is a bit funny here, right? Because usual ADS CFD context, if we want to say there's some theory on some, say ADS3 that just due to the 2D amuse side, that's a bit weird because the 2D amuse is not conformal.
So you're saying there's not even a natural conjecture for what it localizes to?
Yeah, that's right.
That's interesting. Okay, thank you.
There certainly should be one because, just by general law of the ODFD correspondence, whenever you have protected sector in the boundary, there's a sector in the bulk that governs.
On the lighter note, would the sum over wormholes come out?
Sorry?
On a lighter note, would a sum over wormholes be needed?
Yeah.
Okay. Thanks.
Okay. If there are no further questions, let's thank Yifan again.
Thank you.
Thanks a lot, Yifan. Thanks you for immediately after the strings meeting, taking the time out to come and speak to us again.
It's fun. Thanks. Yeah.
It's a very, very impressive work.
Thank you.